Hey everyone, and welcome. So, let's talk about robots. They're everywhere, right? Or at least, they're going to be. We're talking self-driving cars, delivery drones buzzing overhead, robots helping out in our homes. It's an amazing future. But there's this one huge question that hangs over all of it. How do we make sure they're safe? Like really safe? That's what we're going to dig into today. The big challenges, the different schools of thought, and the super clever ways engineers and scientists are trying to build robots we can actually trust.
The biggest hurdle here is just how messy the real world is. It's not some sterile lab where everything goes according to plan. No way. Out here, you've got cars that have to slam on the brakes for a squirrel, delivery drones getting hit by a sudden gust of wind, and then there are us, humans. We are probably the most unpredictable part of the equation. So the real question is, how on earth do you build a machine that can handle all that chaos? How do you make sure it won't fail when it really matters?
All right, so to tackle this massive problem, the whole field has kind of split into two main camps. You can think of them as two tribes, each with a totally different philosophy on how to make a robot do what you want. You've got the engineers on one side and the AI learners on the other.
So first up, let's talk about tribe number one, the engineers. Their main tool is something called control theory. The best way to think about them is like architects. They want to plan everything out in advance. They build these incredibly detailed mathematical models of the robot, its environment, every possible interaction. And this is a big if the real world behaves exactly like their perfect model, they can give you these amazing, rock-solid guarantees that the robot will be safe. But you can probably see the catch, right? The moment something unexpected happens, something that wasn't in their original blueprint, well, the whole system can just fall apart. It's completely lost.
Okay, now for tribe number two, the learners. These folks use a technique called reinforcement learning, and their whole approach is different. They don't bother with a perfect model up front. Instead, they let the robot learn kind of like we do, through trial and error. It tries something, gets a reward if it did well, or a penalty if it did badly, and it just adapts. It's an amazing approach that makes them super flexible. They can handle new situations they've never seen before. But here's the scary part. There's absolutely no built-in safety net. It's all learning on the fly, which means there are zero guarantees it won't try something really dumb and dangerous.
So this is the big standoff, right? You've got the engineers who offer these incredible safety guarantees, but only if the world stays inside their nice, neat little box. And then you have the learners who can handle all sorts of real-world messiness, but they offer, well, no guarantees at all. It's like having to choose between a car that's perfectly safe but can only drive on one specific road, or a car that can go anywhere but might randomly drive off a cliff. What we really want, what everyone is chasing, is the best of both worlds. We want a robot that's flexible and safe.
And this visual really sums up the whole trade-off perfectly. That model-driven approach on the left, that's the engineers. They draw a really clear, hard line, that green circle. Inside that circle, everything is 100% guaranteed to be safe. But outside, who knows? Now look at the data-driven method on the right. That's the learners. It's more of a fuzzy cloud. It's great at exploring, at generalizing into new territory, but there's no solid boundary. There's no line you can point to and say, don't cross this. And that's why the future isn't about choosing one, but about figuring out how to merge them.
Okay, but wait a minute. We've been throwing this word safe around a lot. What does it actually mean when we're talking about a robot? It's not as simple as just safe or not safe. Turns out it's more like a spectrum with different levels of safety we can aim for.
And researchers have pretty much broken it down into these three main levels. You've got hard constraints, probabilistic constraints, and soft constraints. Each one is like a different kind of promise the robot makes about its own behavior.
Let's start at the very top. Level 3, hard constraints. This is the absolute most strict guarantee you can get. It means the robot will never, ever break a certain rule. No exceptions, no excuses. A perfect example is the physical speed limit of a motor. It's just not physically possible for it to spin any faster. That's a hard constraint, an ironclad guarantee. Now let's take a step down to level 2, probabilistic constraints. This is what you see a lot with those learning-based AIs. With this, you can't say something will never happen, but you can say it's extremely unlikely to happen. You can guarantee safety with a super high probability, like 99.999% of the time. Think of a self-driving car staying in its lane. You can be almost certain it will, but there's that tiny fraction of a chance it won't. It's not absolute, but it's still really reliable.
And finally, at level 1, we have soft constraints. This is the most flexible of the bunch. Here, instead of forbidding a bad action, you just make it really expensive for the robot. You program it so that if it does something unsafe, like getting too close to a wall, it gets a massive penalty. This encourages it to behave safely. But, and this is key, it's not a hard rule. A violation is still possible if the AI decides that whatever it's trying to achieve is worth taking that penalty hit.
So now that we get the two tribes and the different levels of safety, we can finally talk about the really exciting stuff, where all the research is going. It's all about getting the best of both worlds, unifying these two tribes to create something new.
And this chart is basically the roadmap for the entire field. Over on the far left, you've got the engineer's world, standard control theory. Great guarantees, but it needs a perfect model of the world. Way over on the right, you've got the learner's world, standard reinforcement learning. Super flexible, but zero guarantees. And right there in the middle, that's the holy grail. That's where everyone is trying to get. AIs that can learn and adapt, but that also come with those strong, provable safety guarantees we need.
So, how do we actually get to that sweet spot in the middle? Well, right now, researchers are pushing forward on three main fronts. First, you can start with a classic engineer's model and then use tons of real-world data to make it better, to help it handle uncertainty. Second, you can tweak the learning process itself, basically teaching the AI to be more cautious right from the get-go. And the third one, which is really cool and what we're going to focus on, is this hybrid idea of adding a safety supervisor.
This safety supervisor idea is just brilliant. You can also call it a safety filter. Here's how it works. You have your super smart creative learning AI come up with what it wants to do. But, and here's the trick, before that command gets to the actual robot, it has to pass through this filter. The filter is super simple. It runs on a classic old-school model that is provably safe. It checks the AI's command and asks, is this safe? If the answer is no, the filter steps in. It can either just block the command or, even better, it can tweak it just enough to make it safe. It's literally like having a calm, responsible adult looking over the shoulder of a brilliant but kind of reckless teenager just to make sure they don't do anything too crazy.
So let's pull back for a second. What does all this mean for the future? Well, it's pretty huge. This is the work that's going to allow robots to finally safely step out of the lab and into our world. And this quote really nails it. It says, researchers have to figure out the when and how to use these learning methods where safety is imperative. What that really means is that the game has changed. For a long time, the big question was, can we even teach an AI to do this complicated thing? Now we know they can. The much, much harder question we're facing today is, okay, how do we make sure they do it safely every single time, especially when they're working right alongside people?
And that really brings us to the big final question, doesn't it? All this work to unify these two tribes is creating systems that are more capable than anything we've ever seen. But as these AIs get more and more complex, as they start to learn and adapt in ways that even their creators can't fully predict, well, it leaves you wondering. If a machine starts to learn through trial and error, a lot like we do, can we ever get that 100% ironclad absolute guarantee that it will always be safe?